Okay, so we'll restart. So one thing maybe that I should have mentioned that I'll mention now. When I wrote this formula of the exponential over the imaginary numbers is like a cosine and a sine. There's another way in which this is very useful. If you're trying to understand things in like circuits and waves and things like this, it allows you now to, if you want to do operations inside the cosine, right? Say take cosine of a sum or products of cosine, things like this. They're much easier to do on the exponential. So many times, if you want to do like shifts in waves, things like this, they're much easier to understand with that that way of writing things, right? So those calculations are done very commonly in say electrical engineering and signal processing and so on. Okay, so that was one of the important features of the complex numbers. Another important feature is that differentiability, like a function being differentiable over the complex numbers, is going to be a very strong property, right? And that's what's really going to make, the theory so nice, right? From the algebraic point of view, the theory is very nice because all solutions have an equation. On applications, the theory is nice because doing spectral theory becomes much easier. Okay, I'm overgeneralizing a lot, but in a sort of an overgeneralizing way. From the analytic side of things, from the analysis side of things, it's the fact that differentiability is so strong that makes the theory so nice. And so the other very important property is a very will be a very strong property. Okay? And this will be viewed in, it will show up in many ways. Okay? And now I'll just write sort of the ways in which it show up, and then I'll try to convince you of why differentiability will be a very strong property without actually proving anything. All right, so this one way that this will show up is in so-called Cauchy's theorem. This is one of the main, it's one of the main theorems in complex analysis that, I don't know, maybe a month from now we'll see the theorem and the proof. It's Cauchy's theorem, which is a consequence in a way of this strong, the fact that differentiability is so strong that allows you to compute many integrals, real value integrals. I mean, in a way, this is what motivated Koshi and others, was there's many integrals I can write over the real numbers that are just nasty to compute, right? But if you think of in terms of complex numbers, an integration over complex numbers actually gets a lot simpler. Then one way to view the fact that differentiability is so strong is that if a function is differentiable, turns out that this will imply that it's analytic. So what do I mean by analytic? I mean, if you can differentiate the function once, you can differentiate as many times as you want, and it will essentially be the same as its Taylor series. Right? I mean, some functions might have singularities, there may be issues, we'll study those, and singularities will be very important, but in sort of a very high-level way, if you're able to differentiate once, you can differentiate as many times as you want, and it will look just like it's some series expansion, which will mean that essentially it's like a polynomial, right? I mean, it will be if it behaves just like its Taylor series, a bit like a polynomial, sure, maybe an infinite degree polynomial, but it looks a lot like a polynomial, and this will be very useful and will make it the theory very nice, right? So this is this series expansion. Right, you'll allow to write functions as just expansions of series. And because of this, will also be the natural way to think about series. Many times when we have to study series, infinite series, complex analysis is the right place to study them. And I'll try to convey why in a bit. Okay. The fact that differentiability is so strong and that all these things will happen is also what allows you to do analytic extensions. Right? So because a function will many times just be equal to its series, say Taylor expansion, then this means that if you know the function in just a little bit of space, right, enough for you to look into what is the Taylor expansion there, then you immediately can tell what it needs to be outside of that space, right? Because you just take, I mean, again, hand wavy, but you could just take the Taylor expansion and then see what it is outside of the space we are in, right? So it allows you to extend functions. Even if functions are only naturally defined in some like small part of the complex plane, you can reason about them outside of there, right? And this is exactly how, this is the most natural way. The first way of proving the prime number theorem involves this idea, right? Where if you want to understand how many primes are there below a certain number, right? The way that we know how to prove this, or the first proof, now there's other proofs, but more complicated, but the most natural proof goes via complex analysis, and exactly because of this behavior. You take, you extend something called the Riemann Zeta function. I'll talk a little bit about it in a bit. Right, and so a very important application of this is an analytic number theory. Okay, and of course, this is just a list just to motivate. It's not at all complete, and I'm not at all describing things with mathematical rigor. Okay. So why is differentiability strong? And again, we'll do this maybe, I don't know, 2-3 weeks from now. Okay, so let's say that we have a function. Right, so a function that is going to go from the complex numbers to the complex numbers. Right, so we think of, f going from z in the complex numbers to f of z. Z is sort of the letter of choice to represent a complex number. And now we want to make sense of its derivative. Right, we want the derivative, f prime, to also be a function from the complex numbers to the complex numbers. Right? But if you think, if you go back to the reals, and you think, okay, I don't like these complex number things. For me, these are just functions in R2, say. And so you say, okay, it's a function from R2 to R2, right? You learned in multivariate calculus a function from R2 to R2. If I want to be able to, reason about its derivatives, write its derivatives, I have to write some Jacobian, which will have 4 derivatives, right? There's basically a derivative for every pair of input-output, right? So there'll be sort of 4 numbers, right, that represent the derivative of a complex number, of a function, if you view it as just as a function from R2 to R2. But here, functions will have to have, being differentiable in a complex plane, will have to have a very strong compatibility condition. And one way to see it is if I write, I want to define the derivative just like how I do over the reals. Right? The derivative on z will be the limit when some, epsilon, in complex analysis, the epsilon is oftentimes an h. When it's like an epsilon over the complex numbers, you'll get used to these notation. Right? This is definitely the natural way of defining a derivative, right? This is how we would do it over the reals. Okay. And over the reals, you might remember that you could think of the derivative coming from the left and the derivative coming from the right, and they might not quite match always, and so on. But if the function is nice, differentiable, and its derivative is continuous, they need to match, right? There's a whole theory in the reals over this. But the situation here is much, much worse, right? Because it's not just that h can come from the left or from the right, right? If I think of z here, right, h can be in any direction, right? I can think of h this way, this way, this way, right, from the positive real axis, from the negative real axis, and so on, right? So h can be any complex number, right? So h itself is is a complex number that needs to go to 0, where both, if you think of h as a plus ib, oh, we have 301. Okay, the problem is fixed. Good. Broke the, yeah, excellent. Okay. Right, so h can come from anywhere in the complex plane, right? So there's a lot of very strong compatibility conditions that need to be satisfied. In particular, if I think about what the partial derivatives look for when h is real valued, or when h is a multiple of I, right? They need to be compatible, right? This value needs to be the same for the limit to exist, right? So for this limit to exist, there's going to be very, very strong compatibility conditions that need to be satisfied, right? So I guess the story is, maybe I'll erase over there so that, right, so in a way, for the limit to exist, there are compatibility. And again, I'm not clearly defining what any of this is, but it's clear that, right, the limit needs to be the same whether h comes like as a real number or as an imaginary number, or anything else in the complex plane. Compatibility conditions need to be satisfied, need to hold, right? And these are famous equations called Cauchy-Riemann equations, and we will derive them. Okay? Although, if you spend maybe 25 minutes or something like this, sitting down and just with this story that I said, you would derive the Cauchy-Riemann equations yourself. But we will do this. Right? Maybe like, I don't know, 2 or 3 weeks from now. Okay, and so it turns out that this will be extremely strong. And in particular, it will imply that if f is differentiable, that f needs to be analytic. Okay. We'll do this, we'll still go quite a bit. We'll still need to work quite a little from going from the Cauchy-Riemann equations to f being analytic. But these strong conditions will enforce that f is analytic. Maybe another thing, okay, to give, for the sake of intuition, maybe another thing is another thing that I should say is that these Cauchy-Riemann equations will be, compatibility conditions between the different partial derivatives, right? So if you think of this as a function from R2 to R2, and if you now look at what these derivatives need to look like when h comes from the reals and the complex numbers, you'll get the fact that they need to match, you get equations. Right? Doesn't matter what the equations look like, but there'll be some equations. And so effectively, f needs to be the solution to some kind of differential equation. Right? And in particular, parts of f will have to be harmonic, and you sort of, all the nice properties from solution harmonic functions and solutions to classical problems in differential equations will apply here. So you'll have things like mean value theorems and maximum principles and things like this. Okay. So the fact that f is analytic, again, extremely hand-wavy, means that f is sort of looks a bit like a polynomial. Right? Or a series. Of course, a series can be very different from a polynomial, but intuitively, all functions that are differentiable will behave a bit like polynomials. Okay? And in fact, with this intuition, we can prove the fundamental theorem of algebra. Okay? So again, what I'm going to do now is not a proof. I'm just trying to motivate what all we're going to do, because today I want to be very hand-wavy. But in fact, it's exactly through this that we can prove the fundamental theorem of linear algebra. So here's the sketch of the fundamental theorem of algebra proof. Okay, so take a polynomial. Okay, this is not a real mathematical argument yet. It will be made into a real mathematical argument later on. Okay, take a polynomial, PZ a polynomial, over the complex numbers. Of course, a non-constant polynomial. let's say it doesn't have zeros. Let's say, right, let's say P of Z has no zeros. And we're going to argue by contradiction, right? The idea is really nice. If P of Z is a polynomial, it's a very nice function, right? If P of Z has no zeros, then the function, say, f of Z equals 1 over P of Z is a very nice function, right? You never divide by 0, which is the thing that you're never allowed to do. So it's okay, right? This is a nice function. Because P of Z is a very nice function, 1 over P of Z, if P of Z is never 0, should also be a very nice function. And so in particular, it should be analytic. And so we should look again a bit like a polynomial. Right? Should look a bit like a polynomial again. Or like a series. Right? But in particular, should be analytic. But now, it looks like a polynomial. However, if you think about what happens when Z goes to infinity, this stays bounded. It can never shoot off to infinity. Right? Because, you know, the leading, if you see what happens at the leading term, this stays bounded as Z goes to infinity. But if it stays bounded, you know, polynomials and functions like this can't stay bounded. If they're bounded, it means that they need to be constant. And so, because 1 over P of Z is a nice function that doesn't go to infinity, it actually needs to be constant. Right? And so, you can prove that 1 over P of Z needs to be a constant. Of course, you know, proving this takes work, right? I'm just saying it now very intuitively, but actually establishing these things will take mathematical work, right? Is the consequence of something called the Liouville's theorem. But the point is that, you know, the fact that complex numbers are so nice from the algebraic viewpoint, actually the way to prove this is actually via the fact that differentiability is so nice. It's via analysis that you prove that the complex numbers are nice numbers from the viewpoint of algebra. Okay, and the proof is this. You need to work, you need to work hard to make it work, but this is exactly the idea. Okay, so let's see what else I want to tell you today. Maybe I'll keep. Yeah, okay, I can do this. And try to go one by one over the. So another reason, mathematical reason of why complex analysis is very nice, and it will be one of the main theorems in complex analysis, will be the Cauchy's theorem, right? So the idea is that contour integrals, so integrals of functions on curves, will become much, much more interesting than they were over the reals. And this, in a way, is also a consequence of the fact that differentiability is so strong. And in fact, this will be the tool to prove sort of all the other results in a way. Right? You establish that differentiability has to satisfy these properties, you sort of use it to prove this statement about integrals, and then you use this statement over and over and over again to prove almost all the other things in complex analysis. Okay, so let's say that I take, over the reals. Let's say I take some integral, something like this. Okay, so you learned, it's now the fundamental theorem of calculus, that this is, so that this is, if f as a primitive, this is just the value of the primitive at b minus the value of the primitive at a. Okay? So, in particular, the nice implication of this is the fact that when you take an integral over some curve, it seems to only depend on the endpoint and the start point. Now, over the reals, that's not very, very interesting, right? Because over the reals, if I want to do a curve, there's not much I can do. I just go on the real line. And so sort of the beginning and the ending point tell me everything about the curve. But over the complex plane, right, if I have the complex plane, right, let's say this is number 1, this is number I, right, I think of the complex numbers as R2, then I can take much, much more interesting curves, right? If I take some curve like this, right, and I call it some curve gamma, then if I take an integral of a nice function, let's say that has a primitive or an antiderivative, fz dz over the curve gamma, right? If I think of a parameterization of my curve and it's equal to the primitive or the antiderivative at a point, at the starting point, or the end point minus the starting point, this, if the curve is closed, this will be 0. Right? But now, while over the reals, this, it was, of course, this is how you compute integrals. It's nice, but it's not that interesting, the fact, if you don't actually know what the antiderivative is or the primitive, you can't really do much with it. But over the complex numbers, as long as the function has an antiderivative, I can actually say a lot, even if I can't compute it. Right? If I integrate around the curve that starts and ends in the same point, and I look at this, right, then I get 0 always. Right? And so this is a key fact. This is known as Cauchy's theorem. Of course, this will only happen over nice domains, nice curves, nice functions. We'll characterize exactly what I mean by nice in these things, but this is known as Cauchy's theorem. And it's probably, the most important theorem in complex analysis. Well, okay, it's hard to say that this is maybe relative, but it's certainly one of the most important. And this is one way to view why complex analysis helps you computing real values integrals. Because if you have a very complicated integral, let's say I have a very complicated integral in the reals. Right? I want to compute an integral from A to B, say. Okay? Of some complicated function. Then what I can use this theorem and I can make a curve, right? I can maybe say, go here, and then complete it with another curve like this. And now I know that the integral over this whole curve is 0, as long as the function satisfies all the nice properties. And so this means that the integral over this curve, or this one, needs to be minus the one from here, right? Or the same if they go in the same direction. And maybe, just maybe, right, we're clever enough to build a second curve where the integral is much easier to compute. And if we do that by computing the integral here, we can actually compute the integral over the reals. Now, if you just look at it, you might think, oh, this is crazy. Why would it ever be simpler to integrate around something on the top than just a real line? But there are examples where this is the case. Right? You may have even seen some of these integrals. Okay, and we'll see one or two, certainly in exercise sessions, probably even more. Yeah. And this is really, these kind of things was really what people were interested in, back in the day, and the reason for Adamar's quote and so on. Okay, what's this? No, maybe I'll. So another important implication of Cauchy's theorem is that it will happen that sometimes the integral is not zero. I won't do any calculation today, but I'll just I'll just try to intuitively describe what might happen. So one issue is that sometimes the integral is not zero. I have some kind of integral like this. Sometimes. And now you can start asking, okay, if this isn't the case, then what can go wrong? When is it, for which functions and curves and so on, can this not be zero? And in particular, it will so happen that if there's sort of a bad point somewhere inside this curve, right? If there's a point here, let's say that this point is this is zero, and the function is, for example, f of z equals 1 over z, right? So this is a nice function away from zero, but in zero is trouble, right? So if I now try to integrate the function around the curve where trouble is inside the curve, then actually this will in general not be zero, right? It will be something else. And for this function is actually not so hard to compute. It will be some multiple of 2 pi I, but I don't want to get into calculations at the moment, right? But turns out that, even though it's not zero, it will still be a certain value and always the same when you go around the curve once. And in particular, you can view this as the fact that it's not zero is allowing you to detect if there is trouble inside of the curve or not. And so it's going to start letting us understand by whether this integral is zero or not, properties, like topological properties of the domain in which the function is nice. So in particular, if the function is nice everywhere besides a point, then evaluating these integrals over curves will allow us to understand things about that domain, right? And we will see that the domain where the function is nice will have a hole in it. And the nice thing is now, if we go on a curve, you say trouble is here. So trouble in complex analysis is called a singularity. So let me use the word, but I'm not defining it yet. It's just trouble for now, right? And if I have a curve that goes around the trouble twice, then basically the value of the integral will be twice what it would be if it only goes around once. Okay, and we'll see this. And if it goes around, say, 3 times and then it loops back once, it will be 2 times the integral if it goes around once. And so this will give rise to something called the winding numbers. Because of the fact that the integral is not zero, when there is trouble inside a curve, you're going to be able to start answering questions of the type, if I have a curve in the complex plane and the point, if I have a function that is trouble at that point, you can now say, how many times does my curve go around it by computing integrals of this type? Right? And so this will allow you to do topology, basically. And I mean, in a very, very, very high level hand-wavy way, this is the start of algebraic topology. Right, because, okay, I guess most of you are going to take algebra this semester, and you'll see the notions of groups and rings and fields and all of that. But now you can think if I have curves, say starting and ending at the same point, something like this, then I can take, right? I can take 2 curves and put them together by go first in one curve and then in the next one, right? So I can define operations among curves. And now the algebraic structure of these operations can tell me a lot about the place where these curves live, because they can count how many times they go around certain singularities or holes in the domains, and this is sort of what gives rise to algebraic topology. And so the point is that Cauchy's theorem will fail if there is trouble, if the function has singularities, or if your domain has holes, and actually this will allow you to understand domains and count holes and understand topology. Right? I don't know how much we'll actually see of this, depends how much time we have, But this is a very important application of complex analysis. Okay, let's see what I make sure I don't forget any nice application. Okay, another nice application of this is in analytic number theory. Okay, so let me just give you a very. I don't know if we'll have time to get to this. So basically, okay, maybe let me say this. Basically, there's the basics of complex analysis that we really have to cover. I'm hoping that this will give us maybe 2 weeks, 2 weeks and a half, maybe 1 week, 1 week and a half in the end to sort of explore, extra things that maybe wouldn't be considered the very basic of complex analysis. And then we can decide what we want to cover. I might use the forum for some kind of polling or something. And at that time, we can go towards the direction of understanding conformal maps and the Riemann mapping theorem, which I won't mention today. We can take in the direction of number theory and analytic extensions and so on. We can go more on the signal processing, maybe sampling theorems and Fourier analysis viewpoint. We can decide when we get to the end, depending how much time we have. But one very nice application of complex analysis is in number theory. Right, and it starts, okay, so I'll be very vague, but it starts with the Riemann Zeta function. So this is a function that you can define for like real values s, bigger than 1, is the following. So you define some series. Okay, so this is just the sum of the reciprocals of the integers to the power s, right? For each s, this will be some number. Right, when s is 1, there's trouble, or smaller than 1, but in general, this will, if s is bigger than 1, there won't be any problem at all. Okay, now a very nice thing is that, okay, maybe before I say the very nice thing, so it turns out that understanding this function allows you to understand the prime numbers and the distribution of the prime numbers. And in fact, this is what what the famous Riemann hypothesis is all about. Okay? It's not obvious why that's the case, I think, at least when I look at it. One way to view why this is connected to the primes is because instead of writing this as a series, we can write it as an infinite product. I won't prove this here, but it will take 10 minutes to give at least an intuitive proof of this. You just work out what the terms are and do some kind of sieving. There's actually, I think it's on Wikipedia, there's a very nice animation that does the sieving and shows why this is true. Okay, so there's another way of writing this function that now it's clear that it has something to do with the primes. Right, because it's a product over p prime of something. So it turns out that this can be used. I mean, okay, very, very vaguely, to count primes. Right? You can use this to count how many primes are there. Right? Because, if you know the size of this, you might be able to argue how many terms are there in the product up to a certain size, write some kind of analysis of this type. Okay, so this allows you to count primes. And this can be estimated with complex analysis. Okay, this is a series. Now this is only defined, for the reals, but there is a way to extend it from the reals to a function that makes sense over the complex plane, except maybe it has trouble in a few points. That's fine. Right, this is the idea of analytic extensions. And so you can use complex analysis to provide estimates of this function. And then with estimates of this function, we'll give you estimates of this function. And estimates of this function will allow you to count primes. And so this is how the prime number theorem is proved. Right? The prime number theorem tells you roughly how many primes are there from 1 to x. Okay? And the proof of this, the first proof, and certainly the most natural ones, come from complex analysis. And this is exactly because of this connection. We may or may not cover this. The problem is that this part estimated with complex analysis, like the conceptual part is very nice, but then there's a lot of actually estimating integrals and so on, and risks me spending 3 hours on the board just like estimating integrals and bounding functions and so on, which might not be the nicest thing to watch. So I'll see if we cover this and just skip a view of the estimations. We'll see. Okay, so let's see if I forgot. I mean, there's so many applications. I'm sure I forgot some, but let's see if I forgot any that I really wanted to cover. I should say, I mean, for those of you that know the Riemann hypothesis, which is probably the most famous open problem in math, just you can view it as trying to get better estimates of this function. In particular, trying to prove that all its zeros are in a certain critical line and so on. Okay, I don't want to get much into it, but if you look at the proof of this theorem and you would like to improve it, that's essentially what the Riemann hypothesis is trying to do. Okay, another thing that I don't think I have time to go into, which is in signal processing, is the sampling theorems. So they're much more natural also in the language of complex analysis, where if I have a signal, right, the signal is something, analog, it's like some kind of wave, but when I measure the signal, I'm going to measure it at certain points, right? So or I keep it in some kind of digital form, where I just have values of that wave at certain points, right? Some kind of discretization. And now you can use complex analysis to understand exactly how fine of a discretization you need, right? And this is the basis, on communication and wireless communication and all this. And it also makes, it's the most clear with complex analysis. Okay, so before we end, I think we have like 5 more minutes. Let me leave you with something to think about. And then starting on Friday, we'll start with actual material, with mathematical rigor and so on. Hopefully, I got you excited about complex analysis, and then we'll actually do the material. Yeah, so this example, I think, comes, I'm sure it's much older than this and showed up in many places, but I particularly heard it from someone who heard it from a lecture of Donald Knuth. So he's a very famous theoretical computer scientist. In a way, is one of the people responsible for the idea of analyzing algorithms. The way that he might have most directly influence our lives is he was the one who created LaTeX, the language to write math in. And he was giving some lecture explaining that complex analysis is very important, and also very important to as a background to understanding analysis of algorithms. And the way that it was arguing this was by arguing that series shows up as a lot when you try to understand, analysis of algorithms, and that series are best understood when in complex analysis. And one way to argue this, right? Okay, maybe because all functions sort of are written as a series and so on, this might help. But one way to argue this with an example is to consider the function. Right, so take this function over the reals. Let's forget the complex number. And now take a series of it, right? Try to take the Taylor series of it. All right, so take like a Taylor expansion of it. You should try it. It's a very nice function, right? I mean, it's like 1 over some polynomial. It has no trouble anywhere over the reals, right? There's nothing suspiciously looking about this function. However, if you take an expansion and you look when does the expansion make sense, you will see that trouble arises at -1 and 1. Right? You will see that if you do a Taylor expansion, things are all very nice between -1 and 1. Right? And here it's very nice, so like the series converges and all this, and then here trouble shows up. Okay? Try to do it and think about why is it that such a nice function, when you take the Taylor expansion, it starts diverging at 1 and at -1. Right? What I'm asking has nothing to do with complex analysis as of now. Of course, I'm asking it because the answer will have something to do with complex analysis. But try to write the Taylor expansion of this, or just look it up if you prefer, and see that it breaks down when you go below -1 or above 1, and try to think about why this is the case. Right? Remember, over the reals, this is a very innocent-looking function, very nice. There's nothing suspiciously looking about it. So yeah, think about this. I want to leave you with this to think about, and then I'll mention this on Friday. One way to explain why trouble should show up at these places, and of course it will involve complex analysis. Okay, I now lost my clock, but I think we're probably around. Yeah, perfect. All right, thank you so much, and yeah.